What specific problem does your work on sparse autoencoders, SAEs, aim to solve in the context of mechanistic interpretability of neural networks, and why is this problem significant?
My work on sparse autoencoders, SAEs, aims to address the issue of understanding the errors produced by SAEs when reconstructing neural network activations, specifically focusing on the predictability of SAE error vectors and norms. This problem is significant because it reveals that a substantial portion of SAE error can be explained through linear transformations of input activations, indicating that there are underlying linear features that SAEs struggle to learn. Additionally, the presence of nonlinearly predictable components of error suggests that certain aspects of model activations are inherently more complex and resistant to simple linear representation. By analyzing these errors, we gain insights into the limitations of current SAE architectures and the dynamics of their scaling, which is crucial for advancing mechanistic interpretability in neural networks. Ultimately, understanding these error components can inform the development of more effective interpretability techniques and improve the performance of SAEs in capturing the structure of neural network activations.
How does the proposed method for predicting SAE error work? Illustrate the process step by step, highlighting the key components and transformations involved in the prediction of SAE errors.
The proposed method for predicting SAE error involves several key steps and transformations. First, the authors establish a linear probe, a **, that maps the input activation, x, to the norm of the SAE error, lvert text SAE error x rvert squared _ 2. This probe is trained using a dataset of activations, achieving high R-squared values between 86% and 95%, indicating that a significant portion of the SAE error norm can be predicted linearly from the input activations. Next, the authors derive a second linear transformation, b***, that predicts the actual SAE error vector, text SAE error x, from x with R-squared values ranging from 30% to 72%, suggesting that while some linear components are predictable, there are also large linear subspaces that the SAE fails to learn. Additionally, they analyze the unexplained variance in the error, termed the fraction of variance unexplained, FVU, which helps to differentiate between linear and nonlinear components of the error. Finally, the authors demonstrate that the predictability of SAE errors is consistent across different SAE sizes, indicating that the method can generalize well to larger models.
Can you provide a simple and illustrative example that demonstrates how linear transforms are utilized to predict SAE error vectors, explaining the roles of input activations and SAE error in this example?
In our study, we demonstrate that a significant portion of SAE error vectors can be predicted using linear transformations of input activations. For instance, we find that by applying an optimal linear transformation, b***, to the input activation, x, we can predict the SAE error, text SAE error x, with an R-squared value ranging from 30% to 72%. This indicates that the SAE error vectors are largely influenced by linear subspaces of the input activations, suggesting that many of the features that the SAE fails to learn are linearly predictable from the input. Specifically, the linear transformation captures the relationship between the input activations and the error, allowing us to understand how much of the error can be attributed to unlearned features. Thus, the input activations serve as the basis for predicting the SAE error, highlighting the effectiveness of linear models in interpreting the behavior of sparse autoencoders.
What are the theoretical advantages of your proposed method over previous SAE error characterization techniques? In what ways does your method improve our understanding or handling of SAE errors?
The theoretical advantages of our proposed method over previous SAE error characterization techniques lie in its focus on the predictability of SAE errors through linear transformations of input activations. We demonstrate that a significant portion of SAE error vectors can be explained linearly, which contrasts with prior methods that primarily relied on downstream benchmarks or simple loss metrics. Our approach allows for a deeper understanding of the dynamics of say scaling and the nature of model activations, revealing that nonlinear components of error are qualitatively different and harder to learn than linear ones. Additionally, we introduce the concept of introduced error, which highlights the architectural limitations of SAEs, thus providing insights into the sources of error that previous methods may have overlooked. Overall, our method enhances the interpretability of say errors and offers a more nuanced framework for analyzing and potentially reducing these errors in future models.
Describe the experimental design used to validate the proposed method. What datasets were employed, and how did you assess the performance of the model in predicting say error norms and vectors?
The experimental design involved using layer 20 activations from the GEMMA 29B model, specifically focusing on 300 contexts of 1024 tokens filtered to include only activations after position 200, resulting in approximately 247K activations. The performance of the model in predicting say error norms was assessed by finding the optimal linear probe from the input activations to the norm of the say error, achieving an R-squared value between 86% and 95% across various say configurations. For predicting say error vectors, the optimal linear transformation was evaluated, yielding R-squared values ranging from 30% to 72%, indicating a significant but less predictable relationship compared to error norms. Additionally, the study employed linear regression techniques and analyzed the variance explained by these predictions, comparing the results across different say widths and sparsity levels. Overall, the experiments demonstrated that while the error norms were highly predictable, the error vectors revealed a more complex structure, suggesting the presence of unlearned features within the model.
What specific results or findings were achieved with your method regarding the predictability of say error norms and vectors? How do these results compare quantitatively to traditional approaches?
Our method demonstrated that a significant portion of say error norms can be predicted with high accuracy, achieving an R-squared value between 86% and 95% across various say configurations. In contrast, the predictability of say error vectors was lower, with R-squared values ranging from 30% to 72%, indicating that while some linear relationships exist, there are substantial linear subspaces that SAEs fail to learn. This contrasts with traditional approaches that primarily focus on downstream benchmarks or simple loss metrics, which do not provide such detailed insights into the structure of say errors. Additionally, our findings revealed that larger SAEs exhibit less predictable error norms, suggesting a complex relationship between say width and error predictability that traditional methods may overlook. Overall, our approach offers a more nuanced understanding of say error dynamics, highlighting the limitations of conventional evaluation techniques.